So module 13 is really, we talked about curved arrows and how they describe reactions. Module 13 is just adding a little bit of language to it. Specifically the language of nucleophiles and electrophiles versus acids and bases. So when I say the words nucleophile and electrophile, break them down. When you see this ending phile, what does that generally mean? No?
That it loves things.
Yeah. So a nucleophile is something that loves nuclei. All right. What kind of charge does a nucleus have? Positive. So a nucleophile is something that loves positive charges. So that's a molecule or an ion that's going to share electrons with other positively charged things. So it seeks out positively charged things to share electrons with. An electrophile, on the other hand, is something that loves electrons. So it loves negative charges. So a nucleophile seeks out nuclei to share with. An electrophile seeks out electrons to share. So when we look at reactions, we're generally going to look for what role each reactant's playing. Is it the nucleophile or the electrophile? And every reaction is going to have both. Oh, I didn't ask a question. We good with the definitions? All right. So here's a couple examples of reactions. All right. In the first case, I have Br minus, so that's got a negative charge. If you're something with a negative charge, are you going to be seeking out electrons, or are you going to be seeking out nuclei? Nuclei, yeah. Because if you got a negative charge, you're attracted to positive charges. So you're going to be a nucleophile. And generally, the arrow starts at the nucleophile, right? Sometimes to abbreviate nucleophile, because it's a long word, a lot of times we'll abbreviate it with just NU or NU and then the Greek letter phi, so nucleophile. That's an abbreviation we'll use a lot. In that first reaction, my second molecule is positively charged. If you're positive, you're going to seek out electrons, right? So that's going to be my electrophile. So the arrow is going to end at the electrophile. So we've seen the arrows before. Now we're just introducing terminology. In the second reaction there, what's acting as the nucleophile? NH3. And the electrophile then is the other molecule. Sometimes we'll get even more specific. You could use the term electrophile to refer to the whole molecule. If you wanted to be more specific, you could say, for instance, this carbon here is the electrophilic site. Right? Just to be even more specific. So that's how we use that language. And when we look at molecules, in general, we think, oh, is this more likely to be a nucleophilic molecule or an electrophilic molecule? So think about what characteristics you would look for to try and decide if something's likely to be a nucleophile or an electrophile. What do you think would make for a good nucleophile? Negative charge definitely is going to be helpful for a nucleophile, right? It's going to be more likely to go out and share electrons if it has a negative charge. Other ideas? All right, do you think something with low electronegativity or high electronegativity is more likely to go out and share its electrons? So I heard low electronegativity. Why would something with low electronegativity be more likely to go out and share its electrons? It doesn't attract its electrons as strongly. Yeah, so good nucleophiles, negative charge is good. Low electronegativity is helpful. Generally, it's good if they have a lone pair, right? We want those electrons to be high in energy. Oops. So high energy electrons are going to be ones that are lone pairs, ones that have a negative charge. Less electronegative is good. Occasionally, you'll see a pi bond act as a nucleophile. So the electrons in a pi bond are less strongly held, so they can act as nucleophilic electrons. But it's going to be less common. So I would look for high energy electrons when I'm thinking about what makes a good nucleophile. The second one that I listed there is not necessarily one you would think of, but smaller molecules are usually better nucleophiles. And here's the reason. If you're going out and seeking a nucleus to share electrons with, it's going to help if you can kind of find where those nuclei are and have an easier time bumping into them. So big, bulky molecules often make really poor nucleophiles because those electrons have a hard time getting at the electrophile that they want to bond with. So, for example, OH minus is going to be a better nucleophile than say this thing, which we would call tert butoxide, because that's going to be a big bulky molecule, and those electrons are going to have a harder time finding the nucleus that they want to bond with. So if you're comparing two nucleophiles, first look at what atom the electrons are on, what its electronegativity is, what the charge is, and then you can compare size if they're similar. We good? So here, I wouldn't copy this chart down or anything, but I just wanted to give some examples of nucleophiles. And this chart is giving you the relative rate in a specific reaction. So this SN2 reaction, this is just a specific reaction where they act as a nucleophile. So the reason I give this list is if you look and think about the nucleophilic site on these molecules, we said negative charge helps. So notice the ones at the top of this list where they're really, really good nucleophiles, meaning they react really quickly. They all have negative charges. The ones at the top of the list also have low electronegativity, right? So those are high energy electrons. Like we said, you get further down, you see some that are neutral, like, NH3 here is neutral. And that's a pretty good nucleophile. You can see when you get down to fluoride, very high electronegativity, not nearly as good a nucleophile, much further down the list. So this list is really going from the best nucleophiles to, let's say, the just okay nucleophiles. So you can see how those factors affect how good a nucleophile we have. All right, if we're thinking about what makes a good electrophile, a lot of them are going to be the opposites, right? What kind of charge would you want an electrophile to have? If something is going to be electron loving, it has a positive charge because that's going to be attracted to electrons. Yeah. So positive charge helps. Having higher electronegativity is going to make something more electrophilic. Something with an incomplete octet. So for example, when I talk about an incomplete octet, what do I mean? What's the kind of thing we've seen that has an incomplete octet? We've run across it a number of times. Well, lone pairs usually fill up the octet of an atom, right? So for an incomplete octet, it's something that doesn't have 8 valence electrons. So that would be, for example, molecules with carbon with a positive charge, right? Because that carbon only has 6 electrons around it, or boron with a neutral charge that only has 6 electrons around it. Those are able to accept electrons and make a new bond, and you don't even have to break an old bond to make space for them. So those are like the best. And if you haven't done Module 10, you might not quite understand what the orbitals that I'm talking about here. But the bottom line is pi star, these would be when you have a pi bond. These are what we call antibonding orbitals. If you didn't do Module 10, you can kind of ignore that part and just focus on the first 3. So high electronegativity, positive charge, and incomplete octet. And when I say positive charge, it could also be partial positive or formal positive charge. And for that second one, again, this is related to like the size of the nucleophile. If there's an electrophilic site in a molecule, but it's all blocked up, there's stuff around it, then it's not really accessible. So for example, oops. If I think about a molecule that looks like this, let's say I have a carbon here that's partially positive, and let's say I have a nucleophile that wants to react with it. How easily is that nucleophile going to be able to get there and attack that positive charge? All right, let me rephrase. So, yeah, think about this. This represents carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen. Is that nucleophile having an easy time? No, it's actually going to get blocked here. So this would be an example of a molecule where that electrophilic site is not very accessible. On the other hand, if I had this molecule, oops. If I had this molecule and my nucleophile wants to attack it, how's that going to go? Yeah, really smooth. Nothing in the way, right? So you want your electrophilic site to be accessible. Have it?
Is the electrophilic site also the name of like where a protein like reacts?
So you could use the terms electrophilic and nucleophilic sites in biology. The question was, does this apply to proteins? So if you've taken biology or AP Bio, within an enzyme, there are often electrophilic sites and nucleophilic sites, and sometimes that's how they attach to their substrate. So yeah, these things definitely are a factor in biology. Yeah. All right, so the last part of Module 13 is really making a distinction between electrophiles and nucleophiles and acids and bases. So in Module 12, you talk about acids and bases. What do you say a Bronsted acid does? Acids they give up a proton. They give up H+. And bases take H+, right? So the distinction between an electrophile and nucleophile is just that if there's an H+ involved, if there's a positive hydrogen atom that's involved in the reaction, then it's an acid-base reaction. If there's not a hydrogen involved, then it's just a nucleophile and electrophile. So a Bronsted base, or a lot of times we leave out the Bronsted part, and we just say a base or an acid. A base is just a nucleophile that specifically attacks a hydrogen atom. And an acid is just specifically an electrophile that's getting attacked at a hydrogen atom. And the reason we draw a distinction here in our minds is because these acid-base reactions where you're transferring a proton, transferring an H plus from one molecule to another, is really one of the most common and the most rapid reactions that we know of. So these are going on in solution all the time. Protons getting passed back and forth between molecules. Whereas reactions between a nucleophile and electrophile oftentimes are less likely to get reversed. They're not happening as frequently. So it can be helpful to draw this distinction in our minds. In Module 12, you learn about how we know which acid-base reactions are going to happen based on pKa values. You can make predictions. Questions about that definition? All right, so let's do just a couple of examples. So in each case here, I have a molecule labeled X. I want you to tell me, is it acting as a nucleophile or a base in each case? So first case, is there a hydrogen involved? All right, if I'm attacking hydrogen, that means X in that case is what? Base, yeah. In the second case, is X attacking hydrogen? No, then we would just call it a nucleophile. Simple as that. So in the first case, we would call that second molecule an acid. In the second case, we would just call it an electrophile. So literally, this terminology is all that's new in Module 13. Other than that, it's practicing with curved arrows, interpreting them, drawing them. We'll close with two more examples. Just look up when you're ready for me to advance. All right, so in these cases, would these be an acid and a base or a nucleophile and an electrophile? In the first one, am I attacking a hydrogen? Nope. All right, so that means that's a nucleophile and an electrophile. In the second case, am I attacking a hydrogen? Yep, so that's an acid and a base. And if you could follow that, then you're ready to do Module 13.